We now come to the end of today's lecture. Today was all about classification. Classification is different to the regression problems we discussed about yesterday in the sense that the response variable, which was a continuous variable in regression, is now a discrete variable. And in particular, we looked at binary classifications where we had just two classes like pass or not passing an exam, having cancer or not having cancer, spam or no spam field. So it was all about modeling those two values classification problems. And the first model we looked at was logistic regression, and we later also looked at linear discriminant analysis and quadratic discriminant analysis. In between, we also discussed several ideas of errors, like we talked about the misclassification error, but we also talked about the confusion matrix, which has all kind of different errors, in particular the type 1 and type 2 errors in there, and we discussed a little bit the importance of those errors and how in certain situations you might be interested more in one or the other. We also talked about the idea of using a threshold for the probability which sets the decision boundary to vary some of these errors and basically make our model more receptive to one of them by, say, setting the threshold very high or very low. We can have some influence on those errors. In any case, if we wanted to talk about how good a model really is, we would have to look at something else, and we discussed the receiver operator curve and the area under the curve as a concept and a measure, a single valued measure, the area under curve, which can be used to describe the quality of the model. A better value for the area under the curve will tell us it's a better model, and then we can choose using the threshold which point on this receiver operator curve we want to use for our specific application. And we said that often there is a kind of cost trade-off which will tell us how do I want to balance off type 1 versus type 2 errors, and where on this curve do I want to sit. In any case, the higher the curve, the better the model, and the higher the area under curve, which is a nice value giving us the quality of the model. And you will see later in the tutorials how you can apply all these concepts in practice. And again, we start off with some simple problems, some conceptual problems, repeating some of the modeling we have done we've seen in the lectures. We're kind of reproducing some of those figures, and then we move into larger real-life examples which are a bit more messy. So at this stage we really want to have understood the concept. One last thing I wanted to mention before finishing. So today we only talked about binary classification. In general, there can also be multi-class classifications. Rather than having cancer or not cancer, I could have classify digits as 1, 2, 3, 4, or classify images as dogs, cats, vehicles, and whatnot. So you can have multi-class classifications, but mathematically speaking, I can always decompose a multi-class classification as various two-class classifications. For example, I could classify for digits, I could classify 1 versus not 1, 2 versus not 2, 3 versus not 3, look at the different probabilities each model gives and choose the one with the highest probability. So really, I can decompose the multi-class classification into various binary classifications. So this is always one way of dealing with it. So even if you only know how to do binary classifications, you can still do multi-class classifications by decomposing them. So in that sense, what you learned today suffices. And in fact, if you do linear models, if you do logistic regression, you do multi-class, this is very likely one way of doing it. But we will also look at different ways of doing multi-class classification when we look at neural networks at the end of next week. So this is all for today.